It's my pleasure to welcome Bhaskar Mitra today. Bhaskar is actually stationed in our London office currently. He's been at Microsoft now about 11 years, is that right? Yep, about 11 years as a scientist in Bing. Somewhere during that time, he switched to being a student about a year or two ago, still while working at Bing. So he's working full-time and completing his PhD at UCL under Emine Yilmaz, who many of us know and have collaborated with as well. He's become one of the leaders in applying neural models specifically to information retrieval problems. He and Nick Craswell have a nice paper, if you would like to read it, that's available on the web right now, currently under submission to Foundations and Trends in Information Retrieval, that kind of compare traditional ways of approaching information retrieval models and where their parallels are in the neural world. And he's going to talk to us about some of his recent work. So with that, I'll let Bhaskar take it away.
Thanks, Paul, for the nice introduction. So today's talk, I'm going to be focusing on some of my research that I've been doing for the last couple of years, both in the context of my work in Bing, as well as Paul mentioned, I've recently become a year and a half back a research student at UCL, so the research in that context as well. This is not going to be a general overview of neural IR, but as Paul already also plugged in, Nick and I have been working on a manuscript on like an overview of the neural IR field in recent years. So this is currently under review for Foundations and Trends in Information Retrieval, but we put up an early preprint online. Nick and I, and also some folks from University of Amsterdam, we've been doing a few tutorials recently this year earlier, specifically Wisdom and SIG-IR. So if you are interested, again, on a broad overview of this area, there's also all the slides and materials from those tutorials are available online. So having said all that, now coming back to the stuff that we are actually going to talk about today. Neural networks. We've seen a big penetration of neural networks in many different application areas. The same is true for IR. If you've been keeping track, for example, at SIG-IR papers, we have seen a pretty big spike in terms of the papers that focus on neural models in last couple of years. The part that, and this also happens to be sort of my personal main focus for my PhD as well as work for Bing. The part that I'm really interested in when I talk about neural networks is that if you look at how neural networks has entered the different fields, what's also has happened is if you look at speech or vision and all of these other application areas, each of these application areas has different requirements and challenges. And they have kind of led to different kind of understanding or innovations in the field of machine learning. So that's kind of my like the area that I really want to get into, where we are thinking about doing machine learning differently based on motivations that based on being motivated by the specific challenges in IR, right? So what do I mean by IR? What would a typical IR task look like? So the most popular IR task that we probably all familiar with is web search, right? So it involves you have a short text query, you have an index of billions of long text documents, and then the search engine fetches you top K documents and presents it to the user. But when I'm talking about information retrieval today, it also includes other IR tasks. So for example, I would refer to query autocompletion, where given a prefix, you're trying to help the user formulate the query by completing the query or recommending possible suffixes for that query for the prefix. It could also include, I'll also give some examples of IR task, where IR task could be like predicting the next query in a search session. So I'll take these three tasks as example for some of the discussions that we'll have during this talk. One of the ways I kind of fit any of these IR tasks is kind of in this kind of a crude framework. So this is very intentionally a crude framework, so bear with me when I describe it this way. But basically, you can think of all IR tasks as you have some input text, which could be a query, could be a query prefix or something else, and then you have a set of different candidates that you want to retrieve from or rank within. So for every candidate and an input pair, you can have some representation of the input and the candidate, or potentially a joint representation, and then from that representation you estimate relevance. The reason I kind of bring this kind of framework up is because while we were writing that paper for FNTIR, this kind of helped us classify how different neural approaches have tried either influencing learning query representations or learning representations of documents, or even just applying neural networks just for estimating the relevance. So for example, the very popular learning to rank framework, the way that would fit into this kind of visualization is that you have an input query text, you have a document text, and then you're generating manually designed features from these two to give a joint representation, and then you can have a neural network or any other machine learning model of your choice for estimating relevance. The part that I am primarily interested in is actually the representation learning part. So and that's what I'm gonna be focusing on during this talk. So, but before I kind of talk about specifically neural models for IR, I wanted to make a slight segue to talk about something that I'm personally, is a favorite topic of mine, to kind of just talk about sort of the basics of different kind of vector representations, and specifically this topic of the notions of similarity in different representations, right? So this slide is really kind of the fundamental, so everybody here knows it, so just kind of bear with me as I quickly go through them. So just defining a couple of things here, local representations and distributed representations. So what do I mean by them? So these are terms that are pretty popular, especially in the neural network literature. So a local representation or a one-hot representation is when you have, let's say you want to represent k different items, then you represent each of these items by a vector of length k, where all the positions are 0 except for a particular position that corresponds to that item. So let's say in this particular example, if I had a set of different items of which 3 items were banana, mango, and dog, then in my one-hot representation or local representation, for banana you have everything as 0 and then one position that has a 1 or a non-zero value, right? On the other side, if you talk about distributed representation, this is the idea of distributed representation is where you represent items by a vector where a particular item is represented by having more than one non-zero items in your vector. A very simple example of this would be if you think of any kind of feature space, right? So imagine I had a feature space where I had features like, does this item bark? Is it a fruit? Is it of a particular shape? Does it have a tail? And so on and so forth, right? So if you imagine some kind of a feature space like that, then you could say that a dog could be represented by something that barks and has a tail, whereas a banana could be represented by something that's a fruit and has a particular shape. The interesting thing about distributed representation as opposed to local representation is that the moment you have this kind of a feature representation, you can actually reason about which items are similar to each other based on the features, right? So for example, in this space, you can see that banana and fruit are similar because they're both fruits, banana and mango. And they are different from dog because they don't have any overlapping features. Whereas if you're talking about the local representation, all of these items are distinct because no vector is similar to another vector in that space. The important corollary here to kind of point out is that the moment you define a feature space, you are in fact implicitly or explicitly making a choice of what items are similar to each other. For example, you could easily come up with a feature space where, let's say, a banana and a dog might actually be more similar to each other than a banana and a mango, right? So maybe your feature space is about, I don't know, some kind of shape, like is it long versus is it round, right? Or something on those lines, or something based on color, by which you could actually say that in that feature space, banana and dog is more similar than, let's say, mango. So my last definition on these slides is about embeddings. So you'll hear a lot of, like, especially in the neural network, all of the papers, embedding is a very popular topic. One of the things that I just want to kind of highlight is that an embedding is a new latent space that retains the properties and relationships between items from an original feature space. So a lot of the work where we talk about, let's say, what to wear glove or other kind of other kind of embeddings that we talk about, one thing to kind of keep in mind is that all of them are derived from an original potentially sparse feature space, and the embeddings basically have the same relationship as in the original feature space. However, your embeddings might be, because of the nature of them being more smaller, dimensional, and dense, they might be generalizing more or other factors, but the important thing is that a lot of the relationships that you, or interesting properties that you're seeing in your embedding space are actually existed in your original sparse feature space as well. Why is this important? This is important because I personally have found that it's quite difficult to reason about embedding spaces because of the nature of these dense vectors. But if you think about the same items in their original sparse feature space, sometimes you can build a lot of other kind of intuitions that can be useful. And I'll give some examples of the same thing, right? So before I go into the example, this is the kind of the question that I wanted to kind of put forward. And this is one of my kind of a pet favorite topic, so bear with me if I talk about this a bit too long. So this is the idea of thinking about, explicitly thinking about what kind of relationships are you capturing in a certain vector representation, right? So let's say you've learned an embedding of words or concepts, and then you have Seattle, and the question might arise, is Seattle similar to Sydney because they're both cities? Or should Seattle be similar to Seahawks because of Seattle Seahawks, right? So I wanted to take some example and actually kind of answer this question about like how some of the choices you make in designing or how you learn your embeddings would actually influence which of these relationships you're actually modeling and your embedding space actually captures, right? So what I'm going to do here is I'm going to take a really small toy corpus of 16 short sentences, and once I have, and from those 16 short sentences, I'm going to try and derive different kind of representation for the 4 terms, Seattle, Denver, Broncos, and Seahawks, right? And basically my goal here is to show that depending on how you featureize these words based on this corpus, you actually end up capturing different kind of relationships between these 4 terms. So the first thing I'm going to do is I'm going to featureize these words based on which documents they appear in, right? So we see that in document, for example, Seattle appears in document 1 and 2, Seahawks appears in document 3, they both appear in document 5, and so on and so forth. Just a quick note on the colors here. So the white here means a 0. The gray means a non-zero value, and the only reason I have a light and a dark gray is to indicate those columns where you have more than one non-zero element. So the dark gray basically shows where there is some overlap between at least 2 of the vectors in here. So basically, if you kind of squint at this particular diagram hard enough, you start seeing that Seattle, the vector for Seattle, based on this very crude rudimentary example, actually starts looking very similar to the vector for Seahawks. And similarly, if you look at Denver and Broncos, they start looking similar to each other. For people in IR, this immediately would remind you of the term document metrics that you would typically factorize with for LDA and other representations, right? So now let's do a jump and do a very different kind of featureization based on neighboring words, right? But with one small additional detail that I'm actually going to consider the distance between the 2 words. So what do I mean by that? What I mean by that is that I have a feature Seahawks +1, which means that this is a feature that says that on one position to the right, the word Seahawks appears. So for Seattle Seahawks, you have a non-zero value because somewhere in here you have a bunch of Seattle Seahawks that you see in your corpus, right? So then you also have, let's say, let's take the example Seattle Seahawks Wilson. So the word Wilson actually ends up giving you two different features, Wilson +1 and +2. So Wilson +1 means it occurs one position to the right of this word, which is true for Seahawks. So you will see that Wilson +1 actually is a feature for Seahawks, but not for Seattle. But Wilson +2, which means it's two position to the right, is a feature that's non-zero for Seattle, but again, it's 0 for Seahawks, right? So you take this feature space, and now again do the same exercise of squinting really hard at this diagram, and suddenly you start seeing that Seattle and Denver starts looking similar, and Seahawks and Broncos starts looking similar, right? So this starts giving you more of a notion of kind of a type-based similarity in this diagram. By the way, for people in NLP, this is also, people refer to this for a pretty long time as kind of syntagmatic and paradigmatic relationships. So I'm kind of using a different term, but I mean something very similar. The third version is similar to the previous one, but we do one change where we no longer consider the distance between the words. So now Wilson is a single feature that's true for both Seahawks and Seattle, right? And again, if you do the squinting thing again, what would happen here is now we actually see that pretty much all four of them has some kind of an overlap. And like Seattle is similar to both Seahawks and to Denver, but because of different sets of features, right? And this, if you kind of think about it, this is exactly the kind of feature space that something like word2vec or glove operates on. So the point that I'm trying to drive towards is that if you think about this feature space, you realize that it's the property of which words are similar to each other, or the fact that something can do a vector algebra in the embedding space is actually coming from this original feature space. So this, for example, Levy and Goldberg did this work where they showed that the vector algebra like king minus man plus woman, you could actually do this on the sparse feature space without even learning the embedding stuff. And similarly, it doesn't really matter if you're using matrix factorization or neural nets or some other approach. The relationships you're modeling is actually much more influenced by basically what original feature space you're trying to compress. This, by the way, one of the things about word2vec is the window size that you consider when training word2vec actually kind of has some strong influence on the balance between the type and topic-based similarity. So basically, if you think of this, this is the reason why in the word2vec embeddings, you would see Seattle being close to both Seahawks and Denver. So it has a mix of this type and topic similarity, and how much it is type versus topic might depend on different the hyperparameters, for example, like the window size and stuff, which I'm not going to go into details, but we can talk about why that is after the talk. So this was I wanted to jump into this example because this often is pretty intuitive when you look at this visually like this, but then obviously the questions come up, why is this important, right? So why are we talking about this in the context of neural IR? This is important especially because, so if you think about the IR problem, but I mean, to be honest, this is true for anywhere where you use embeddings, not just in IR. But taking the example of an IR task, what you would typically do is, given, let's say, an input text like a query or a prefix, you could come up with some projection into an embedding space, and then your assumption is that the neighbors in that embedding space are the good results or candidates that you want to rank high and show to the, show to the user. Right? So what that also means is that for a particular input, if these are all my right candidates, then it means that these right candidates should also be similar to each other. Now, if you're talking about different IR tasks, so we talked about in the beginning like document ranking, query autocompletion, or related search, the argument that I'm really trying to make is that each of these different IR tasks expects different notions of similarity between the different items that they're trying to rank. And it's important to understand what relationship you've modeled in your feature space and whether or not that's appropriate for the task that you're trying to apply it to. So going back to the same three examples, so let's say my document ranking example is that the query is cheap flights to London. And let's assume these are the titles of the documents that I'm ranking. So cheap flights to London obviously should be relevant to the document cheap flights to London, but then obviously you don't want to see documents about cheap flights to Sydney or hotels in London, right? However, if you take the query auto-completion task, imagine this is also modeled in a similar way where given a prefix, I have some prefix embedding that projects into a space, and then I'm doing a nearest neighbor search for based on suffixes. So I'm just ranking suffixes. Let's assume that's how we do the query auto-completion task here. So here, now what happens is if you have the prefix cheap flights too, you actually would, as you expect, London and Sydney to be the right, I mean, they are potentially right answers here, right? So what that means is that in this space, if you've learned a representation, London and Sydney should actually be close to each other, whereas they definitely should not be close to each other here. On the other hand, London and Big Ben should not be close to each other here, whereas here you could potentially rank a document high that also mentioned Big Ben, right? So this kind of very kind of a topical similarity versus type similarity. And then when you talk of next query suggestion, there's a whole lot of other things that opens up. So for example, here, the same topic is obviously relevant, but you're also trying to predict the next step in the task. So here there's almost like a directionality factor as well. Like you can think of certain pairs of queries where query B would always follow query A and not the other way around. So for example, if you see two queries like the big clock tower in London and Big Ben, you would probably expect that the big clock tower in London query came before Big Ben, because it kind of indicates that the user did not know what it's called, right? So yeah, so there's a potentially different kind of relationship that you would need for doing this particular task. I'm going to stay on this topic a little longer by showing another single model trained on 3 different types of data that kind of presents these 3 different types of, demonstrates these 3 different types of relationships. So this is the very popular, the DSSM model. So again, given this, people here should be pretty familiar with this model. Excuse me. Oops. So the DSSM model is a Siamese network. It was originally proposed for the document ranking task. The way this model, what this model basically does is it takes a query, it takes a document title, it projects the query into some embedding space of 128 dimensional embedding space, it projects the document title in the same space, and if the query and document are relevant to each other, then you would expect the distance to be small, the cosine similarity to be high. And the way you train this model is you take a query, a positive or a relevant document for that query, and you take a bunch of negative documents which are not relevant to the same query, and you train to optimize cross entropy at the top to predict the right document from the negative documents. Right? So now we take the same exact model. The model doesn't really specify what text, like you could present any pairs of short text here and train this model. So let's take the same model and actually train it on 3 different types of data. So we're going to train this on query document titles, which is what was originally proposed. We are also going to train it on prefix-suffix pairs. So we'll take a query, split the query randomly at a word boundary, and then train the model on, given a prefix, predict the suffix. And then the third one is to actually take pairs of query from search sessions, and then given a query, try to predict the next query in the same session. And basically what you end up seeing is that if you've trained the query, let's take a particular example, let's take the 2 models trained on query document pair and prefix suffix pairs. Once you finish training the model, you take the query model from the first set, you project a piece of text in the space, and then you look at its nearest neighbor. And on the other side, you take the query that was trained on prefixes, and you do the exact same thing. You've given a piece of text, you project it using this model, and then you look at its nearest neighbors. And you almost immediately see this pattern, especially, by the way, if the models are trained on short text, you start seeing this. Sorry, this was not for short text. Ignore that last comment. So what you immediately start seeing is that the model that's trained on query document pair, the nearest neighbor to Seattle is like weather Seattle, Seattle weather, IKEA Seattle, everything about Seattle. Whereas if you look at the model that's trained on prefix-suffix pairs, its nearest neighbors are all these other cities, Chicago, San Antonio, and Denver, and so on and so forth. Right? Similarly, if you project the query or the piece of text Taylor Swift, the model that's trained on query document pairs gives you everything about Taylor Swift, whereas the model that's trained on prefix-suffix pairs, it actually gives you everything that's of the same type as Taylor Swift, like celebrities, right? So again, kind of the very same idea as we were looking at before. Sure.
How do you train the prefix suffix pairs?
So you basically take a query corpus. For every query, you randomly split out a word boundary, and then you would pass the prefix here, and the suffix here, and some negative suffixes here. So the actual paper that this one cites, this is where we were looking at suffix prediction given prefix for dealing with auto-completion for rare prefixes, where you actually haven't seen any query with this prefix. If you still had a candidate of, let's say, 100,000 most popular suffixes, then you might still be able to predict which suffix goes with the prefix.
Do you have two different networks on the left and right?
Yes. So this SAMIS network, what's happening is it's actually, you have two different models. So the weights are not shared between this and this, but this is the same model here.
Okay.
Right?
One question.
Yeah.
So if you go back to the previous slide, it seems like, sorry, the one before this. Yeah. It seems like there are two things going on from what you said earlier. One is the supervision signal of what's related. And then the other question is the co-occurrence of different words, and a different approach that people often apply, right, is you take the embedding, so take some general embedding, embed these things, and now use the supervision signal to actually learn for each of these domains so that you don't conflate both of them. Going back to your earlier example, right, if the relationships are there in the embedding, then one thing you can do is just project to the right relationship. And there's a separate question of, are the relationships even there in the first place, and are you getting, how much do you get from each of those?
The other thing is also that you might have learned an embedding with certain relationships that's almost so orthogonal to the task that you are trying to learn, so one example is, in Bing, when we were working on autosuggest, somebody took a particular embeddings that was trained basically to capture topical similarity. So it was trained on basically query and documents. And then what they wanted to do is they wanted to actually use that for auto-completion. But what they did was they initialized the embeddings based on what was pre-trained, and then they did continued training. And they actually realized that it was worse than randomly initializing the embeddings. Because what happened is, if you think about it, if Seattle is close to Seahawks and far away from Sydney, but in the query auto-completion where somebody says map off, where Seattle and Sydney should be close together, this embedding had to actually push these two things apart and pull those two things that were far away close together, right? Now, if that's your only representation of these items and you're just trying to learn a function on top, then it depends on whether the original embedding space has captured the useful information in addition to capturing other stuff. But it could also be that the original embedding space is completely the wrong space, that there's no other function you can apply on top to recover the actual useful information that you're looking for, right? So it depends. And basically the argument I'm trying to make, I was going to have that slide after this, is that all of this really matters if you're going to learn representation separately and then use it for a different task, which is actually pretty practical because a lot of time you don't have enough data for the supervision signal to do the learned representation. Representation learning takes a lot of data. So that's where people, for example, would train what to vec on the document corpus alone, and then you might plug in those embeddings in doing ranking or something else. So that's when it becomes important to think about, is this even the right thing? Or if the thing doesn't work, then when you're debugging, then it comes to fact like, okay, maybe there's a disconnect between the embeddings I've learned and the task that I'm trying to apply it on. Or it gives you ideas about how to learn the right relationship so that it might be more useful for the task. So, and it doesn't matter if you're learning everything end to end, then this question goes away. The third example I wanted to show was the case where the model was the same DSSM model is now trained on pairs of queries from search sessions. And this again shows very different kind of regularity. So here you can actually see a similar kind of regularities that you might have noticed. You can probably make the connection with like the word to vec at a term level. So this basically allows you to do similar kind of vector algebra on short text like you could do with word to vec on terms, right? Because you see that Denver to Denver Broncos is parallel to San Francisco, whoever the team is, sorry. There you go. Seattle to Seahawks. I should always stick to Seattle because I know the answer. And yeah, so this basically, if you train it on session query pairs, you can basically then use the same model to do things like University of Washington minus Seattle plus Chicago gives you Chicago State University. Obviously, this like any other vector algebra based solution obviously is not always going to be correct. So you also have like wrong answers sometime here, but it just kind of shows you that it has a similar property. And if you think about it, this models of training on pairs of query in a session or training on prefix suffix are actually similar to word to vec, where it's training on neighbors. Whereas the original model, if you think about training from query to document, is more like training like an LDA model where it's term to document ID. So it's kind of has the same kind of intuitions that pops up. So yeah, so I skipped, I mean, I kind of said, prematurely talked about this side, but this is the kind of the main point that you really care about all of this if you are going to use pre-trained embeddings. If your model just learns your embeddings in situ for the task that you're doing, then you can be completely ignorant and let the model learn whatever is the right representation. So I want to give an example quickly of where this could be useful. This was actually joint work with Eric Nalesnik. He was an intern here, and Rich Caruana and Nick Craswell. So this basically kind of led us to kind of thinking about using word embeddings for document ranking. So in document ranking, one of the things that you could use these embeddings for is sort of soft matching or, so for example, let's say we have these two passages and we want to know which of these two passages is more relevant to the query Albuquerque, right? So there's a lot of hints if you look at the first passage from the fact that it has words like metropolitan, population, area, and so on and so forth, right? So if you knew some way you could determine the other words you expect in a passage or a document that correlates with your query terms, then that can be a useful signal for relevance. Unlike typical IR models where you only count the exact occurrence of query terms in the document. And you can say that the second passage is not relevant because, yeah, this passage is actually taken from Wikipedia, described from the Microsoft page, Wikipedia page on Microsoft that just happens to mention Albuquerque in there, right? So you take this idea. So what you can then do is you could, given a query and a document, you could represent all the query terms using the word embeddings that you have. You can represent all the document terms with the embeddings you have. Let's assume you just do a simple centroid of the query terms, centroid of the document terms, and you have a simple cosine similarity or a dot product to say if the query and document is relevant. Let's say that's the simplest model you can do, right? Now, the interesting, and this is where thinking about these relationship explicitly might help you is like, so when we started thinking about this, one of the things we suddenly realized is that if you look at the word to vec model, there's actually two different embeddings that are being learned. So the word to vec model, what happens is you have an input word represented as a one-hot vector, multiplied by a matrix, multiplied by another matrix. This is the bottleneck layer. And then you're trying to predict the correct neighboring words, right? What happens here is that you actually have two different weight matrices. And I'm going to, for ease of reference, I'm just going to call them the in matrix and the out matrix, or the in embeddings and the out embeddings. Typically, once a word to vec model is trained, people completely discard one of these matrices and just use the other one as the embedding, right? Now, if you train your word to vec model on short text, for example, like queries, turns out looking at two words a similarity between two different terms based on both of their in embeddings or based on both of their out embeddings actually gives you a notion of similarity that's closer to a type-based similarity. So Yale becomes close to Harvard, NYU, Cornell, and so on and so forth. However, if you were to represent one of the terms with in the other terms with the out embeddings, and then do the dot product or cosine similarity, you end up, the neighbors of EL starts becoming faculty, alumni, that is misspelled anyways, orientation, and graduate. It took me 2 years to realize that's misspelled there. That's something. Anyways, so and what you are, for document ranking, what you're really looking for is, if you have the query YEL, you're looking for a document that not only has the word YEL in it, but likely also has other words like faculty, alumni, and orientation, and so forth, right? At least you expect that more than occurrences of Harvard and NYU. Although Harvard and NYU's presence might also indicate some kind of relevance. So basically what we did in this case is we plugged in this intuition into the word embedding model we showed before by basically doing something very simple. We would use the in embeddings for the query terms and the out embeddings for the document terms, so that when you do the cosine similarity or dot product between the query and the document, you're basically computing an in-out similarity for every query term with every document term. And that gives you an improvement in relevance in this context.
What is it? The input is a word and the output is the next word?
Yes, so the word2vec is typically trained given a word, predict another word within a given context window.
Including itself or not including itself?
Not including itself. So it's basically, let's say, if the window size is 10 words on each side, it would try to predict each of the 10 words on either side of this particular word.
How does that compare to using the DSSM setup?
You mean in performance-wise?
Yeah.
Well, the DSSM would perform better just because it's trained specifically for that task, right? And the DSSM model is learning a topical notion of similarity.
Because with DSSM, it looks like you're trying to map the query to the document title. Here you are expanding the query in a sense.
Yeah, so I should clarify. I mean the DSSM model trained on query document pairs. If you look at the DSSM model trained on prefix-suffix pairs, it's basically learning a similar relationship as word2vec training on word and neighboring words. So again, you can use even that model. So we haven't really worked on this, but there is no reason why you can't actually train. If you had, for example, small amount of query document pair of data, you can actually train the DSSM model on prefix-suffix pairs and use it in the same in-out way as the DSM thing kind of proposes for document ranking as well.
And in that case, you're training on queries?
Yes.
Okay.
This model was trained on queries.
I see.
So basically, the two secret things here is that if you train this model on long text and have the window of text long enough, then even the in and out starts becoming more and more topical. The balance moves towards it. So basically, the reason this model, this becomes important is you actually get a big benefit by training on query terms as opposed to document text. And for short text, the in and in-out similarity, actually the difference becomes bigger. So you combine the two things and then you see a big improvement. But if you were to train this model on, as I said, long text with long context window, then you might see a less difference on this.
So if you build these sort of models that can kind of give you a score of the next word given the previous word, what happens if you create like 10 slots in a sentence and then run belief propagation to fill in the 10 slots? Can you generate sentences that way?
So this is similar to, so the word2vec was originally proposed as a simplification for RNNs. If your goal is only to learn an embeddings, but this is basically goes back to the same idea of sequence completion, right? And depending on a few different things, so for example, you could train word embeddings where the word appearing next to you is different from the same word appearing 2 positions away from you. So you could actually take that into factor, and again, that would change the relationships you're learning. But in terms of sequence completion, yeah, this basically goes back to the RNN and all of those kind of work directly.
RNNs, but just using this statistic to generate sentences by simply running loopy belief propagation through the slots.
You could. You just have to, in that case, also take into context then the position and the distance. But there is, you could come up with I mean, again, if you start doing that slowly, it would start evolving into something that starts looking like RNN. So basically the point with RNN is that I want context of not just the previous or the last 3 or 4 words. I want to have longer and longer context. So the whole RNN LSTM is about how can you have some notion of the things you've already seen in the sequence with a fixed memory size.
I'm just asking for intellectual curiosity, I understand what RNNs are. I'm just curious what will happen if just belief propagation. So nobody has done it.
so as opposed to RNN, like you can always have a model that has, if you knew your sequences are always short, you could come up with a model that always knows that there are at max k items before, and you have an exact memory of what you've seen in the past, and then you're not doing recurrence, but you actually have different weight matrices based on positions farther away. And yeah, I've never worked in that space, so I wouldn't comment on like what works or what doesn't, but I'm just saying that. Sorry?
And you don't know if anybody has tried that just for fun?
I'm pretty sure in the NLP space people have, but again, I would probably defer the question to somebody who's worked in that area. So yeah, so moving on further, a bit faster.
Wait, go back. What was the data that's available?
So we actually put out the in-out embeddings data for 2.7 million word trains on Bing queries just publicly. We had released it.
Is anyone using that currently?
I've had questions from different people, so I assume some people are. But yeah. This was another joint work with Fernando and Nick. So basically in the same spirit of looking at word embeddings, the other question that came up is that obviously terms are inherently ambiguous. And this is one of Fernando's favorite topic, and he's really convinced me that this is a very important thing to think about, is to kind of think about this idea of local and global analysis, right? So the point is basically that, let's say you learn a representation globally based on your whole corpus, and so then you basically learning some sort of a crude representation for every term, especially when the term is ambiguous and can take different meanings, right? And this is not just like the crude apple computer versus apple the fruit, it's also very subtle. Like for example, the word cut could mean different things, but then if I know that I'm using the word in the context of gasoline tax, then this cut means like cutting tax or like reducing deficit or whatever, right? So basically the idea was like, how can you get really extreme in thinking about a local sense of a term or a representation of a term? So what we did is we tried this experiment in the area of like query expansion for retrieval. So what we would do is, given a query, we would send that query to the index, get a bunch of results, and then we would at runtime train a word-to-vec model on that corpus of top 1,000 documents, and then use that embedding to expand the original query, send it back to the corpus, and get results. And basically the point comes down to is this. So what this diagram shows is the blue dot in the center is the query centroid. And the way you're expanding the query is by finding other terms that are similar to the query center. So basically you're doing a nearest neighbor around this space. Every other circle in this, these are just control lines, but every other circle here are the terms, candidate terms that you can use to expand the query. And the red terms are the actual good terms that we know that if we add this to the query, you would see an increase in NDCG. And that's what it looks like for a global word vector space, and this is what it looks like for the local vector space, right? But the idea here mainly is that, I think this actually relates to a slightly broader idea that for any kind of modeling, if you learn so for example, when you're learning a query document ranking model, all these neural net models are basically starting to encode real world information about correlations, right? So if you say, somebody says, let's say Albuquerque, right? So you expect that for the word Albuquerque, you would expect these things like altitude or population or area as to be the correlated words that you would expect in the document. But these models are always going to be inferior to a very, very narrow topic like something specifically in microbiology, right? It's very hard that this model can memorize those correlations. And the idea was that we could think of actually training models potentially at runtime or doing things differently such that these models can still go in and effectively research a particular topic, learn a new representation, and then apply it to a problem. It's the metaphor that I use with Nick is kind of thinking about whether your model is a librarian or a library. Can your model practically learn everything about everything in the whole universe and be a library? Or is it like a smart librarian who might not know enough but knows, given a question on microbiology, that's the section on microbiology, let's go there, let's read up all the books, learn a new representation, now I know which book to look at, and so on and so forth. So that was kind of the idea, but this was a crude way of doing this.
Embedding is trained on different data.
The local embedding is, so given a query, it actually retrieves a top 1,000 documents, and the embedding is trained on those 1,000 documents.
The global one has not been trained on that data.
It has been trained on a random sample of documents from the same corpus.
But
not for the query specific.
The same data.
Yeah.
So it isn't like Because usually when they talk about this embedding, they're saying, well, all the information is there, you just have to find the right projection.
Yes, but the
in
whole
this case, it's all actually different data, so you may not even be able to find the projection.
So the point is, even if your corpus is fixed, it's almost impossible for you to learn on everything in the corpus within. So this also goes back to thinking about your model having certain amount of capacity, and it's going to prioritize learning things well that it sees more often and not learn those things that it sees rarely. Whereas if you knew all you wanted to do was to answer this question about microbiology, you could go find only those 1,000 documents on microbiology. So there's enough data, but the model basically doesn't prioritize if it has to learn the whole universe, but then it can go and learn that small universe much more efficiently and be more effective.
So that's hard to tell because these are very high dimensional embeddings, so you have space for everything. So
technically, yes.
Maybe numerical issue that you talked about or whatever.
It could be. So there might be something that you could do to force this. There might be other solution to this, but yeah.
So let me come back to the question on different data. I mean, the local is just a subsample of the global, right? So it's not different data. It's a subsample.
It's different. It's actually
a different sample. It's not different data. It's not different documents. It's a subsample. Local is a subsample.
But they're two different samples.
They're different samples. They're not different data, right?
Well,
if everything was learnable from the global, then you would still have the relationships there. Global has access to everything local has.
If the global is big enough to get the samples, if you train on all the data.
No, local is a subset of global.
And not if you sample. If you sample, you will not get anything that's in the tails.
You train global over everything, or
it trains over everything, but it is subsampling from the overall distribution because.
Yeah. So initialize the seeds, and you can do a subset relationship. Same thing is done in learning curves.
Basically,
right?
The idea is that global might have a lot of noise, so some of the subtler relationship may be drowned out by noise. So and then you kind of apply like two-level ranking, where you use some sort of naive textual benching type of stuff to discover a likely relevant subset, and then you hope to discover locally strong relationship from that subset. Is that kind of a reasonable way to look at it?
Right. So basically, your global the model is it's any model that you train on some data is going to prioritize learning things that it sees often. But then you can use, for example, the global model to get some ranking of basically narrow down which domain this belongs to. And then you can have a local model that's trained on that domain specific data. And then it would likely perform better on that specific topic.
So if I understood what you said previously, when you sample the global corpus, you will have many fewer documents on microbiology than when you sample this local corpus. Yes. So you don't see the same data in the two cases.
Yes, it's true. Having said that, I would still imagine that if you did train on the exact same samples, but like subsample, I think this would still hold. But what you described is what we had tested.
If you just take the global data and then add the local sample to it, then the question is, those are two different questions, right? Would you then have a problem with learning and still ignore that data just because, but in this case, you're not even seeing it, so that's...
Potentially, yes.
Yeah.
Okay, so I'm going into the last part of this talk where this is more recent work where we actually started looking at deep neural nets trained end-to-end, so no longer thinking explicitly of these representations and all that stuff, but having deep neural nets and kind of a very clean setup and training them for document ranking. And obviously this is all based on the fact that we have a lot of data in Bing, so we can actually train these models end-to-end on our ranking data. So what we started looking at was the kind of a classical document retrieval task where you have a short text query and a long text documents. A lot of the models in IR today actually looked at short text versus short text. And one of the things to kind of realize is the challenges of doing short text to long text are different, both good and bad. So short text to short text, these embedding based models actually benefit a lot from the fact that short text to short text, the vocab mismatch problem is much more severe. So if your model understands synonymy or related things, it's more likely to show you improvement over exact matching based similarities. On the other hand, for long text, the opportunities lies from the fact that long text has mixture of many topics, and the matches could be actually in different parts of the document, and based on which part of the document matches, it might indicate more or less relevance, and also things like term proximity and all of those other things becomes important. So there's a lot of possibility of modeling other stuff when you're dealing with long text, not just the vocab mismatch. An interesting way of thinking about this neural nets for IR is to take these two particular queries. So these are my favorite poster child queries, Pekarovich Land Company and what channel are the Seahawks on today. So the point that I want to make with this query is Pekarovich Land Company, if this is the term Pekarovich you've never seen in your training data, then I don't care how you have your neural model input representation. So for example, it could be one-hot representations of terms or character trigrams and whatnot. Your model never going to have a good representation for the term Pekarovich. So even for DSSM that takes character trigram based inputs, you would expect that for a term it has never seen before, it would probably have some sort of a random projection or not so very informative projection, let's put it that way. So the point is that for this query, for an embedding based model, it's actually it really struggles with a query like this, right? On the other hand, we know that typical classic IR models actually really do well with this, because if there are like 50 documents in your billion index that has this term, then fetch those 50 documents, rank them based on where these terms appear and how they appear next to each other and so forth. But you could learn all of the same functions with a neural net. On the other hand, you have the query, what channel are the Seahawks on today? Here, a lexical matching model would actually suffer because the right document potentially doesn't even have the word channel in it. It would probably has actually terms like ESPN or Sky Sports, right? So it's almost like a translation model kind of thing happening here. If you see these words in the query, you expect these other words in the document. So this is where an embedding-based model is likely to really shine. And one of the first work we did in this space was this thing we call the duet architecture, which was basically just the simple idea that, hey, why not, if these are the two different aspects that might be important in IR, why not use a neural net to learn both of them and learn them jointly? So that basically led us to this idea of the duet model. Now, this is an architecture we propose, but then the idea of the duet goes beyond just this architecture. You can come up with other architectures that has the same duet property, that you explicitly are mapping, learning the lexical matching as well as the semantic matching signal for retrieval. And the final model in our case was basically a simple linear combination, and you're learning this whole thing as a single model jointly on your supervised data, where basically it has query, document, and labels. So trained like typical learning to rank models are based on pairwise laws. How do these things differ, right? So the local model, it's trying to learn how to do lexical matching, exact matching. It has no interest in learning any kinds of representation. So the input representation is such that it cannot even learn any kind of embeddings in this case. So what's the input representation look like? So this is a really simple matrix representation. So think about a query that has 4 words and a document that has 1,000 words. So the input representation for this submodel is a query words by document words matrix, which is a binary matrix, and it's non-zero every time the word matches the document. So this means that, for example, if you look at this line, slightly shifting line, it means that you actually saw the occurrence of big deal derby as a phrase in that document. And if you look at these documents here, these examples, it almost visually suddenly becomes clear which documents are relevant and which are not. So the relevant documents has more matches. It has more matches towards the beginning of the document. It has more phrasal matches. It definitely has matches for all the words in the query, unlike this guy, and so on and so forth, right? So you can see these visual patterns from these metrics that then you can imagine that you can train a neural net on top to basically learn what are the good patterns of matches.
You're like ignoring term frequency completely in this representation?
Term frequency, no, but inverse document frequency, yes. Term frequency you can get by actually just counting along this line, right? So if the neural model can just count the number of lines in here, and it knows the term frequency for each of these terms. So what we did is, again, you can have different kind of architectures, but the simplest thing we did is we had a convolutional model on top. One of the important thing was to have the window of the same length as the document. Basically, it turns out one of the important thing is for it to map how early in the document you see the occurrence. That was an important thing. But other than that, we tried different things. They didn't make too much difference, but I'm sure there are things here that you can explore. But basically, you're doing a convolutional model that runs over that same matrix that I showed, and then it has some more fully connected layers and so on and so forth, and it gives you a single score.
The length of the document. Then there's no convolution.
It moves along the query direction. It's moving along the query direction. So on the other side,
Along the query direction.
yes. There's some things about term proximity. Just because of time, I wanted to maybe go faster and then we can come back to the questions. But I'm skipping some things about term proximity on the query. So, sorry, going the wrong direction. So now on the distributed model, what it does, so this again, if you're familiar with the DSSM work, this model is similar to the DSSM with some changes just to kind of deal, to specifically deal with long text. So what this model does is it takes the query and then projects the query into an embedding, and then it takes a document, but instead of projecting the whole document in the embedding space, it actually takes a window over the document and projects each window to an embedding space, compares the query embedding with the window embeddings, and then it aggregates all the information at the top and gives you a single score, right? So this is a very simple way I'm describing this model. Details, for more details, you can always look at the paper. So yeah, so basically we then trained it in a very similar way as the DSSM model. You would have a query, a positive document, and a bunch of negative documents. You train it to maximize cross-entropy loss. We had a bunch of different findings, but one of the main things we found is that, and this was kind of expected, is that the part that really takes a lot of training data to learn is the text representation. So the local model or the lexical side of the model actually doesn't benefit too much from being thrown a lot of training data at it, whereas the part that focuses on learning embeddings is the part that actually, so for our first duet paper, we didn't even converge. We basically trained it for like 24 hours or 36 hours and kind of stopped at that point. But basically, if you look at the training curve, it looks like it was still going up. So we could have had a lot more better NDCGs by training it longer. And the only reason we didn't is because of time. We later ran the same model on Trek complex answer retrieval task where the data was smaller and my training time was faster. And there we actually got to a point where it kind of flattened off at something around like 32 million samples or so on. And this is one of the important points why if you look at a lot of papers in academia today, it's kind of unfortunate, but a lot of focus is on lexical matching model just because of the lack of big data sets for training these supervised models. I'm going to skip this slide. This is also out there, the implementation's out there publicly on GitHub. But this led us then, this is the kind of the last recent work I wanted to make a mention of. So we had another intern, Ahmed, who came in from UMass earlier this year, and he looked at, again, deep neural models. Given we had a lot of data, it was something he was interested in to, again, look at deep neural models for IR. And the problem we looked at is the fact that it's not just documents in web search, it's not just body text, but it's also title and URL and anchor text and click streams and all the other kinds of data sets that we have, right? So this work was basically kind of the same kind of you can compare it with like going from BM25 to BM25F. So basically, how can you use a neural model that when you think of document as a single piece of text, but now my document is composed of multiple fields. So how do you go from, how do you have a neural model that actually can make use of multiple fields? So this is a wisdom paper, 2018. So basically, the idea is this: you have a document that has title text, URL, body, incoming anchor text, and incoming query text. And what you're doing here, I'm going to just give you a quick overview. So basically, I'm kind of touching upon the main design decisions that make a big, that makes a big difference. So you learn an embedding for each of the meta streams separately, because each of these fields or meta streams might have different properties. So you want to learn different embedding spaces for them. For fields that have multiple instances, so for example, for anchor text and query text, you have multiple clicked queries associated with this document and multiple anchor text associated with this document. You are effectively doing an average pooling, but making sure you take care of how many instances are there and do the right averaging. So by doing all of that, you end up with these field embeddings. And then you actually you learn different query embeddings to match with each of these different fields. And this comes from the fact that, for example, the query embedding you want to learn to match with title might be different from the query embedding that you want to learn to match with URL, because they capture different properties. Once you've done this Hadamard or element-wise product between these two embeddings, you end up with a match vector corresponding to each of the fields. So this comes from the intuition from similar intuition as BM25F, where you don't want to combine the different fields based on individual scores. So this is the same idea that you could end up where, let's say the query was Barack Obama Facebook. By having a vector and not a single score, it allows you to the model to realize that maybe Barack Obama matched on every field, but Facebook never matched on any of the field, versus Barack Obama matched on this field and Facebook matched on the URL field. So by having a vector, it can encode that information, but it wouldn't if you had a single score there. And then you have some fully connected layers on top to combine this. And one of the things that's important in this context is, and this happens even for typical learning to rank model, is that if you have a very strong, precise signal such as click streams, it can actually hamper how well you learn the other fields. So one of the things that we found really useful, especially in the presence of a field like click data, is to have a field level dropout in this model. So yeah, so that's basically it. So basically one of the things I want to kind of, on a concluding note, wanted to say was, so these deep neural models, obviously there's a lot of excitement in the field, and people have been thinking about how this is going to influence the IR field in general. My personal observation is that all of the stuff that we typically talk of IR initially went into designing of features during the learning to rank days. And now when we are starting to talk about these deep neural nets, the same intuitions, core intuitions from IR is actually fueling the design of these different architectures. This one I'm not going to talk about, but we've also done recently some work on proactive recommendations, such as proactively recommending attachments for email. And yeah, these are all the papers that I covered, and thank you. Sorry for going a bit over time.
So we have time for questions, or if you want to step out, you can step out quietly.
Those convolutional network filters, what do they look like? I didn't quite understand how you built that up, but it seems like it would be very interesting to see what these filters are like.
So for the local model, the disclaimer is we didn't spend a lot of time doing too many experiments, but one of the things we did find was to have the length same as the documents. So yeah, so basically the way we had this was, we would assume we had 10
different lengths.
Yeah, so we assumed that we made some simplistic assumptions of saying there are 10 query words, 1,000 documents, 0 padding if there is less, truncation if there is more, and then a window of 1 by 1,000, and moved it for this.
And the window is 1 by 1,000.
1 by 1,000. So that's query words being 10 and 1,000 being the document words. So it's the length of the document and moving towards in the query direction.
So then you're not capturing that thing that you're talking about, where you get these lines.
Yeah, so what happens here, that's a good question, is it actually does get captured to some extent, but again, you can do, this is just having a single convolution, you can do different kinds of convolution and combine these things. But even in this case, it does get captured crudely, where what happens is by having a vector here, it can still, if you can just hypothetically, this vector could capture that this term matches a lot in the beginning versus later in the document. So this vector could encode such an information. It wouldn't encode exactly if they are next to each other potentially, but yeah.
You could do that if you had like 3 by ND, then
you could do, so you could do other convolutional configurations in addition to having something that captures the whole document length. We just didn't go into that space, but I'm pretty sure you can do a lot of different architectural stuff here that would show.
To make it as long as a document so that you don't have any shifts this way?
Yes, so that's basically because we noticed that it actually learns that if you have the query terms appear here in the document, it's much more important than if it appears later in the document,
Sure,
and
but
that's
you can
important enough.
capture that in the next layer.
It could. Well, we actually had run a few different experiments where this showed up. This is obviously kind of the explanation is a hypothesis that that's maybe what is happening. But we did see that it made a big difference in having this.
And then have you thought about filling this up not just with co-occurrence, I mean matching of the words, but some sort of a measure of similarity using some
Yeah, so
events?
there is other work, and if I'm not mistaken, like the match tensor paper from Facebook and others, they've tried other architectures where you basically have the lexical and semantic, and maybe you have the same kind of an like a matrix representation that captures both, whether the terms are exactly same.
About 3 or 4 different things.
Let me go ahead and see if we can do a few more, because Bhaskar's available all week. And
Yeah.
I think maybe a longer conversation with Nabosa might be in order.
I'd love to. Yeah. So
Are there
I'm happy to
a
chat.
few other questions?
So I had a question about the local versus global model you were talking about. So it looks like the way I understand it is that it's a neural version of pseudo feedback, basically. So did you compare it to traditional methods trying to do pseudo feedback?
Yes. So actually, Ahmed I think Ahmed and Bruce actually wrote a paper where they basically, again, so this wouldn't improve over pseudo-relevance. This would not perform better than pseudo-relevance feedback, but they combined it with pseudo-relevance feedback and showed that it improves on top. But that's exactly correct. But so this paper was written in the context of query expansion, but kind of the core idea that Fernando and I, especially Fernando, was really trying to put forward is this whole point of like learning a model specific to the situation you are in. And so basically learning at runtime and going from that, but it was tested in that context.
So I have a follow-up question related to that I know that I'll talk to you about later was, when pseudo-relevance feedback fails, it typically fails badly. And if you have a bad starting model, you're going to do poorly. But it seems like you could use this in 2 places, which is, why bother to use the pseudo-relevance feedback? We have query logs that have click information, which give you weights on which one should be the focus for any query we've seen before, how to expand for that query. Or even in a session-based case, using the previous click documents in the session to expand for the next query, right? Where we know things stay topically constrained. Have you looked at or thought about either of those? Okay.
So maybe I didn't get your
So
question.
the first one is, for any query we've seen before, instead of looking at the top 1,000, you can do a click-based weighting, stat click-based if you'd like, to look at those documents. That's going to be much more targeted at relevance and not have the failures of pseudo-relevance feedback. So we can do expansion for any query that we've seen before. And the second case is you can do the same thing on a session-based example, which is the documents that somebody has clicked before the current query is your case of what's relevant to this topic, right? And we know that people stay topically relevant within a session. Again, you're in a much better case by not doing pseudo-relevance feedback.
So 2 different answers. So one is in terms of the first part of that, I think this whole point of local global analysis, if you think of the spectrum, the local analysis becomes really interesting when you're dealing with a query that has effectively no presence in your click data. And yet, so for example, the Pekarovich land company, you would expect that if there are even 50 documents in your index, it might fetch those 50 documents, and those 50 documents might be enough for you to learn a local representation and do something interesting. If you have enough presence of that in click streams, you could imagine that the global representation might already capture a lot of it. Of course, there might also be a sweet spot in between where it has some coverage from click data, but not enough that your global intersection, like the global representation, does a good job. So maybe you can use that. Yeah, you can definitely use that. The second part about looking at previous documents in the same session. Again, I've not looked at it in the context of document ranking. But one of the things we've chatted briefly before that I was super interested, but haven't really made a breakthrough there is, so when I was training the DSSM model on pairs of queries from session, the intuition that I really had was kind of starting to think about search sessions as effectively a path in an embedding space. And if that's going to allow us to do something interesting in that direction, right? And that was trained on queries, but it could also be trained on queries and click documents and whatnot. Again, I haven't done anything on that. It's something that's been on the back of my head. If anybody's interested to chat about that or has any ideas about that, I would love to talk about.
quick follow-up to the follow-up.
Last question.
The top 1,000 documents, you're using L2 ranking or?
This was based on INRI. So he was, Fernando
You're
ran
not
this
using
on
tech
INRI.
data?
No,
Basically.
not in
You're
here.
using the full search engine ranking.
Yeah, no.
You would
This,
be incorporating
no,
tech
this
data.
was just based on retrieval on just something simpler model. That's an important question, by the way, which I'm not going to touch upon, is how you evaluate these models, especially the deep neural models on top. There's this whole discussion about telescoping evaluation versus other things, but I'm going to refrain from that. We can talk about it separately, but it's actually an interesting question.
Second speaker again.